So we have seen a public key crypto system that is not used in practice. That is the knapsack public key crypto system because it is broken. But now we can see an example which is constantly used in practice, which is RSA algorithm. So in order to understand how RSA works, we need a little bit of number theory. And actually, we won't go much further in the details, so I will just give you some results from number theory, and by using those theorems or corollaries, we can understand why RSA encryption and decryption works. So let's start with Euler's phi function. Let n be an integer, then the number of positive integers that are less than n and relatively prime to n, in other words, greatest common divisor of n and c equals to 1, is given by phi n. So you can, phi n actually gives you the number of integers that are less than n and they are relatively prime with n. So one easy thing to see is that if you choose n to be a prime number, since it is prime, nothing less than p and larger than 1 can divide it. So phi n would be n minus 1 when n is prime. So let's see how phi n acts when we have composite numbers. So let n has prime decomposition as follows. So these pi's are prime numbers. So you can actually write any integer in this form as a multiplication of some prime numbers and some powers of them. So this is a prime decomposition. So then phi n becomes phi of p1 to the ai times phi of p2 to the power a2 and so on. So, and you might think that what is phi n when p is a prime? For a prime number, if your input is p to the power k, then phi pk equals to pk minus pk, p to the power k minus 1. Sorry. So this means that we can compute Euler's phi function for any integer. First, what you need to do is to get the prime decomposition. So you get this, and you can compute each one of them by using this formula. So it is not that hard. But in our case, n will be the multiplication of two prime numbers, which is p times q. So it will be easy for us to compute what phi n is. But anyway, we need to give the general definition so that we can work on the specific cases. So let's move on with some results from elementary number theory. Let p be an odd prime. Fermat's theorem says that a to the p minus y is equivalent to 1 modulo p. So this is a good observation which we are going to use for primality tests. So we already mentioned that a decision problem and a search problem is somewhat different. And in the primality testing, we try to figure out if a given number is prime or not. So it is a decision problem. And in those kind of tests, we are going to use theorems like Fermat's theorem, or we are going to use Euler's theorem. It is somewhat similar, but this time p minus 1 is divided by 2, and the result is given in this form. But this is a special notation which is called Legendre symbol. Sorry. So Legendre symbol is defined as follows, and it is given as a over p. The result is 0 if p divides a. Result is 1 if a is a square in fp, which is the Galois field defined by p. You can think it as the positive integers with 0 that are less than p. Okay, and it is minus 1 otherwise. So it is kind of a generalization of Fermat's theorem. These results actually have the following corollary. A to the phi n is equivalent to 1 modulo n. And this is the thing actually that we are going to use for encryption and decryption in RSA. This actually would explain us why the decryption works. But anyway, we needed this introductory results from elementary number theory. Okay, let's keep this in mind and move on to RSA. So I will define it in its basic form, because in practice we need a mode of operation like we did for block ciphers, but basic form is easier to understand. So let's see how it works. So let's start with the key generation. What you do is first randomly choose big primes P and Q. So in practice we are choosing prime numbers around more than 300 digits or so. So actually this step is not that easy, as you can imagine. So because we don't have an algorithm that runs fast and gives you a big prime, right? Otherwise we wouldn't have this largest prime searching computations and so on. But we have some tricks that we can use, and we can actually perform these operations really fast. And we can choose two big odd numbers with a high confidence that they are prime. And we will see this step in primality testing. But let's assume that we have a good way of choosing big prime numbers P and Q. So this is your first step. Next you do is multiply P and Q and obtain N. Third step is to choose a number E, and this can be chosen like 3 or 2 to the 16 plus 1, as I said before, in a different algorithm, which would make computations a little bit faster. But it should be the greatest common divisor of E and phi n should equal to 1. So at this point, we see Euler's phi function again. So we need the value of phi n. But as we mentioned before, n is just p times q. So phi n is actually phi p times phi q. And if you go back to the definition, this would mean that phi n is actually p minus 1 times q minus 1. That's it. So next step is to compute the inverse of E modulo phi n. So you might think that this might be a hard problem. By the way, when we talk about modular inverse, this means that D is such a number that when you multiply it with E modulo phi n, you obtain 1. So an inverse in modular arithmetic means that a number that makes, after multiplication, that makes the result 1. So inverse of E is D, means that their multiplication results in 1 modulo phi n. So again, you might think that this is hard to find, but we have an extended Euclidean algorithm which computes this number in a very fast way, regardless of how large the phi n is. So that's it. Actually, at this point, you obtain public key parameters n, which is the multiplication of the two big primes that you have chosen, and E as which you choose initially. So n is referred to as RSA modulus, and E is referred to as RSA exponent, and these are public. So what are private? D is private, so D is calculated as the inverse of E. So you might think that if an attacker knows E, can they capture D from there because they know E and N? But as we mentioned, in order to perform this operation, the attacker needs to know phi n. In order to know phi n, they need to have the decomposition P and Q. So if the attacker can capture P and Q, so as I already said that phi n is just P minus 1 times Q minus 1, then the attacker also can use the extended Euclidean algorithm to compute D. So at this point you can see why the security depends on the factorization problem, because if the attacker can factorize n and obtain p and q, then RSA is broken. But if they cannot, then RSA is secure. Actually, this is one of the ways of breaking RSA. So as you can see, private key is D, but we also need to keep P, Q, and phi n secret. Otherwise, by using this knowledge, this is actually the trapdoor. By using this knowledge, the attacker can also obtain D. So this is the key generation. We have the public key and the private key. So let's see how the encryption works. So assume that somebody wants to send you the message M, and these public keys is announced publicly, so everybody knows the N and E you are using. So what they do is to compute e to the power of M modulo N and send you the result. So this is encryption, as simple as that. So for the decryption, what you do is when you receive the ciphertext, you compute the d to the power of it modulo N, and magically this transfers you back to M. And we will see in a minute why this is the case. So as you can see, it is just modular taking powers modulo N for encryption, and for decryption, it is again taking powers modulo N. And at this point, you might think that this encryption process is really hard to perform in practice because, for instance, N is a very huge number and E might be a huge number, and your M again be a huge number, and taking this power and then taking the modulo might sound very time consuming, but actually we have some algorithms like square and multiply and so on, which makes this process really fast. So it's not that hard to perform in practice, and actually we are using it in practice all the time. So why this works, why taking the d to the power of C returns back you to the original message. Let's see why this is the case. So let's consider the initial case, so case 1, where the greatest common divisor of M message and the modulus N is 1. So if this is the case, then what we are doing is when we receive C here, then we take the d to the power of it. But C itself is M to the power E modulo N. So this means that what we are dealing with M to the power ED. But we chose E and D so that they are equivalent to 1 modulo phi n. So this actually is a number that can be written as 1 plus k times phi n, where k is some constant that we don't know, and it doesn't matter. So if you write it in this way, like m times m to the phi n power k, by the corollary I showed you, this m to the phi n modulo n is always 1. So this is 1 to the power k, which is also 1. So this actually becomes 1, and the result is m by the corollary. So it is as simple as that. But when the greatest common divisor of m and n is not 1, we need to check some more stuff. But as you might imagine, it is hard to get such a thing because, if you remember, n is just p times q. So somebody has to accidentally send you a message which equals to p or q, right? Or a multiple of it. So first we need to check if m divides pm. So if it does not divide m, then m to the ed modulo p would give us m modulo p again by the Fermat's theorem, because p is prime. And in the second case, if p divides m, then m would be equivalent to 0 modulo p. Again, this operation will give us m. So in both cases, m to the power ed again equals to m modulo p. Similarly, m to the ed equals to m modulo q. So at this point, if you use Chinese remainder theorem, this would mean that med would be equal to m modulo p times q, which is n. So decryption works due to number theory. And I need to mention one thing more here. I said that this is RSA in its basic form. So you might think that what is missing here. The missing thing is as follows. As you can see, if somebody wants to send me the message M, what they do is to take the e power of it and send the ciphertext to me. So if I only use this operation, then somebody who captures the ciphertext a few days later send it to me back again. So when I decrypt it, I will get the message M again, and I will thought that they send me the message M, but the person who is replaying this ciphertext don't know what M is. So for instance, if somebody says hello to you and sends you this ciphertext, some other people send you the same ciphertext and keep telling you hello and so on. So this is why we need and so when two messages are the same, the ciphertext would always be the same and so on. So in order to avoid it, we actually choose a random value for each of our messages, and during the encryption we use that random value so that such replay attacks won't be possible, and every same message would have the different ciphertext because we will be adding some random value there. Okay, so let's talk a little bit about primality test. We said that P and Q should be generated randomly. So actually one of the security depends on here. We said that initially you need to choose big random primes. So we already had a lecture about randomness, so you know what we mean by random here. But the problem is how we can choose such big primes. So in the next video, I will explain what is used in practice and what kind of algorithms we have so that we can use and check if a given number is prime or not. And we will actually be using randomized algorithms there.